Hi class, in this recording we're going to be focusing on PhysioEx exercise number 5, activity 5. And in activity 5 we will be looking at the effect of radius on pump activity. So as we change the radius of our blood vessels, how will that influence the activity of our pump, or in this case the activity of our heart? So as we work through the activity, it's worth emphasizing some key terms that we need to be familiar with. We have systole and dystole. Dystole is when the heart is relaxed. Typically the left ventricle is what we care about, so the left ventricle relaxes. Systole is when the ventricle is contracted. And we have end diastolic volume and end systolic volumes. The end diastolic volume is the amount of blood left in the left ventricle when it is done relaxing. The end systolic volume is the amount of blood left in the left ventricle after it is done contracting, or after the end of systole. And the difference between those is going to be the amount of blood ejected from the heart with one contraction. This is known as stroke volume. If you know stroke volume, the amount of blood ejected for one beat of the heart, or one contraction of the heart, and you also know the heart rate in beats per minute, then you can calculate cardiac output. Usually stroke volume would be given in units of milliliters per beat. Heart rate will be given in units of beats per minute. And those two terms multiplied equal cardiac output. Please make sure to memorize this equation of cardiac output. As we're looking at the activity, you're given a scenario in your PhysioEx exercise where we have some blood in the lungs, we have a pulmonary vein carrying blood back to the heart, we have a heart represented by that central cylinder, and then we have an aorta, and then we have blood of the systemic circuit. And I personally had a couple glitches while I was working through this, depending on my web browser. Sometimes Chrome worked, sometimes it didn't work as I was working through this simulation to get my data. If you are running into a situation where it's not working, try a different web browser. So instead of using Chrome, try Firefox, or just refresh the page a couple times. Usually that's all it takes to get it to work. As we look at the data for chart number 5, or for your experiment, this is what your data will look like. We have flow rate increasing. The radius of that left tube of the pulmonary vein was unchanging. We would increase the radius of the right tube, or the aorta, so we increase that variable. Stroke volume remained constant. The blood pressure remained constant on both sides. So we had 3 columns that were changing. We had the radius of the aorta, or the vessel leaving the heart. We had the stroke rate, or the heart rate, and then we had the blood flow out of the heart in milliliters per minute. As we altered the radius, as we increased the radius, the heart rate also went up, and the flow rate went up. And what we find is that the graph has a positive slope to it, or a direct relationship. As radius increased, flow rate increased. So let's talk about the position of the pump during dystole, or diastole, I should say. That pump in the middle represents the heart. So there's our pump right there in the middle. And this pump in the middle during diastole is going to correspond to the heart relaxing, and the pump will be at the top. So the piston in the pump will be elevated. So as it's pictured right here, this is diastole. So the pump, the cylinder is filled with blood. Question number 2, describe the position of the pump during systole. In this scenario, the pump would be depressed all the way down during systole of the left ventricle. So we would have just finished contracting our heart, or contracting our pump. Question number 3, describe what happened to the flow rate when the blood vessel radius was increased. Let's go back to our data. As the blood vessel radius increased, our flow rate also increased. Question number 4. Explain what happened to the resistance and the flow rate to maintain pressure when the radius was increased. So that was a typo here. Think flow rate instead of pump rate. What happened to resistance and pump rate when radius was increased? So if we think of radius, increasing the radius is going to reduce resistance. And if we have less resistance, it's going to be easier to push blood out of the heart. So here, as we look at our data, if radius increases, we have less resistance, and we find that the amount of blood being ejected from the heart per contraction will increase because there's less peripheral resistance. And if our stroke volume remains constant, so I highlighted the wrong column there. If our stroke volume remains constant so that we don't have that increase in blood, it'll still be easier for the heart to contract because our heart will be able to have less resistance so it can drain itself faster. So in this scenario, the way the PhysioEx was pre-programmed is that as we reduced peripheral resistance, we find that the heart can eject blood quicker and the heart rate will increase. And if stroke volume is held constant and the heart rate increases, the flow rate will increase. So what happens to the flow rate to maintain pressure as the radius was increased? The flow rate goes up. So if we have less resistance, flow rate needs to increase in order to maintain constant blood pressure. That's all we have for activity number 5. If you have any questions or comments, please feel free to post them on the class discussion boards. And as always, happy studies.